네, 한성민 씨 안녕하세요. 네, 정상목 씨 안녕하세요. 자, 아직 박건우 씨는 안 오셨나요? 네, 안녕하세요. 다 오셨군요. Okay, let's get started. Okay, so this is already lecture 10. So I think that more or less we are already covered 1/3 of our entire semester. So now it's time to start a new subject. Up to now, we have talked about how can we consider a general two-dimensional structures. So that was our main topic in first 10 lectures, and I think that we have already covered that all. So main point was if we have multiple regions, then we have to consider unknown variables corresponding to each region. And for certain points where two regions are meeting together, so we call them as interface nodes, then obviously we can have two different variables at the same physical position but with different material property. Of course, we can assign certain relation between these two quantities. In many cases, the relation is two quantities are the same. But in some cases, we can introduce certain differences between two quantities. And another one is assigning one relation for the relative distance between these two numbers and the original equation we have to consider. For example, Poisson equation or electron continuity equation that is merged into our representative node. So if we have two vertex nodes corresponding to one interface node, then we have to assign two equations. One equation is the equation of our interest, and second one is the relation between two quantities. So that was the main message up to now. So now we will move to more related with the physical model itself, and the contents covered up to now is more or less not covered in our book, Introduction to Computational Electronics. So I think that it was a little difficult to find out some resources, but anyway, that was a really good exercise to you because anyhow you have to deal with this general two-dimensional or even three-dimensional meshes. But anyway, now let's come back. So from now on, we will start the most important simulation method in our field, computational microelectronics. So what is it? that will be the drift and diffusion. So we will talk about this one, but not in a fully formal way, but I will just introduce the resultant equations because you are anyway belonging to this field, so introductory material is not required in my opinion. But anyway, if you have any questions, please interrupt me. Then usually when we say drift diffusion equation, so we consider three equations. So three equation means that here, we have to consider Poisson equation. One Poisson equation and electron continuity equation. And finally, we have to consider whole continuity equation. Okay, then by collecting them all, then we can find a closed set of equations, and that is typically called as the drift diffusion model, drift diffusion equation, drift diffusion scheme, whatever. So there are many different names for specifying this system, but anyway, we call it as drift diffusion. So Poisson equation, as you may find in our previous, means that my recorded lectures. So Poisson equation is just a purely mathematical term for representing or categorizing certain equation, and in general it's like this. If we have a certain unknown variable and its Laplacian operator is given by certain source term, so which can be a function of a position, then this specific form is called as the Poisson equation. But you know, in our case, in our consideration, our so-called Poisson equation is simply looks like this. Okay, this is not actually the Poisson equation itself, and this is just Coulomb's law. However, if we introduce a certain approximation for our displacement vector, so here D, which can be written as permittivity multiplied by electric field. Yes, so from here to here we just expect a simple media, and if we go to further, then we can introduce this kind of approximation. Of course, from here to there we have to introduce the electrostatic approximation for our electric field. So that's the reason why this quantity is called as the electrostatic potential. But anyway, when you just put them all, then we will find that minus epsilon and gradient of phi equal to rho. So this is the form actually we will use in this course. But you know, when the people are trying to first solve this kind of equation, at the time the epsilon was just a constant. So think about this one. You are just solving the gallium arsenide sample or just a silicon sample. In that case, you don't have any oxide or any insulator in it. So the epsilon can be considered as a constant. So only when we can expect or we can assume the constant epsilon, then the equation can be reformulated in this way. So when you have a look at this form, then you can find that it completely fit to our Poisson equation. Yes, it is the Laplacian of our unknown variable, and here we can have a source term which depends on the position. So it perfectly fit to the definition of Poisson equation. So the pioneers in this field just call it as Poisson equation. It is because it was really the Poisson equation. However, after that, we now consider insulator. So if we introduce insulator, of course, this epsilon is now much different from that of silicon. So no longer we can pull this epsilon out from this spatial derivative operator. So we have to keep this form, but due to the historical reason, so we just call it as the Poisson equation. So please note that whenever I say Poisson equation, although that is not exactly the Poisson equation, I'm just calling this equation. Okay. So if you have any question, then please ask me question. So now let's move to the continuity equation. So continuity equation is simply given by this form. Okay, first of all, think about, in my opinion, even whole continuity equation can be considered in equal base. So think about this one. Let's call this C, which can be either electron density or hole density. You know it. So think about this one. This is partial derivative of carrier density with respect to time. So since C can be a function of position, of course, and function of time, when I say partial derivative with respect to time, it means that, okay, R is fixed. So we just keep the observation point, yes, let's say that this point, and we are just looking at this point and just counting the density, or counting the number of carriers inside this small position, nearby small position. Then after time elapse, what will happen? More electrons or less electrons? So if we have this one, then let's assume that electrons are approaching and entering into this observation point. Then what will happen? If we have such a system, then we will say that, okay, if we have time variation, then we will have increase of carrier density, because yes, the box is given and electrons are coming in, so we will have the increase of C density. Okay? But think about the opposite way. So when you just make an observation on this point and say that net flux of carriers in outward, so escaping from this point, then what will happen to our C density, carrier density? Then we can easily understand that will be negative. So simply speaking, if we consider this one, the total outgoing flux. So the flux escaping from this observation point is really related with our time derivative of C. However, if we have a positive outgoing flux, then that will be reflected to the minus of lambda C over lambda T. Okay, if this quantity is positive, then okay, carriers are escaping. So carrier population or carrier density should be reduced. So we have a minus sign, and if we have a negative total outgoing flux, it means that actually carriers are coming in and immigrated from outside, so we will have a positive value. So it's good to have such kind of interpretation. So simply speaking, I wanted to write down in this way. The general form of continuity equation should be written as lambda C over lambda T equal to, yes, minus times total outgoing flux. Then how can we formulate this total outgoing flux without writing in this plain English? But how can we write down in a mathematical form? That can be done by this way. Okay, so let's just think about a flux of our carrier. So F sub C can be either F sub N or F sub P. So depending on your carrier, and just integrate this flux over our area. So now we can consider this surface integration. So can you understand? So let me just repeat once again. Now we have a box which is chosen to estimate the C density. Then, yes, for this box, we can consider 6 surfaces or 6 faces. Okay, so sum of these 6 faces is corresponding to A surface. Yes. So then just to integrate the surface integration over this small volume, then we can define, for example, yes, here we can think about the flux, and here we can think about the flux of carrier. Also we can think about flux of carrier. Yes, when we have such a kind of a computation, then summing them all or integrating them all, then that will be exactly corresponding to the total outgoing flux. So our students, so please let me know you have understood up to now. Then okay, so of course I have to say here left hand side and right hand side of our equation is not perfectly balanced, because you know C is just number per unit density, and now we have introduced the time derivative, so you can expect the physical unit of the left hand side will be the number per unit volume and unit time. But if we consider this right hand side, then what will happen? In this case, we have here flux, which is given by number divided by unit area and unit time. And how about this dA? This is area, so we have square centimeter. So by combining them all, then we can find that currently the right hand side just looks like this. The overall unit of this quantity is simply given by number per second. Then what is the difference? Here, left hand side, we have additional per volume quantity. So what is the difference? So we have considered in the right hand side term, we have considered a small box, and when we consider the left hand side, we have not considered such a box. So we have to consider here the volume of our box. Let's call it as omega, whatever. But anyway, that is the volume we have to consider. Actually, C times omega will be the number of C carriers. Okay, so we will have this relation, so everything looks perfect. Okay, so simply speaking, this will be the general form of our, our continuity equation. Then you know that we can make a little further manipulation. So how can we manipulate them? Let me just follow a little further. Okay, so now we have a surface integral of certain quantity. So then how can we make this transform from this surface integral to the volume integral? And you can easily understand. So now instead of this surface integral, now we can define the volume integral, and now we consider this volume infinitesimal volume integral. Then what happens to this one? Here we have to introduce divergence of our flux. You know it. This is mathematical identity, so you can easily understand when we have such arbitrary vector field, then that transformation can be justified. So now we have this one. Then let me just finalize our discussion about this form. Currently we are talking about a small volume called omega, and its surface is called as A, and then for that situation we will have omega, and that will be given by this form, omega and Fc R. However, if we make the volume of omega as a really small, quite small, then variation of this divergence term will be quite small, because we are just still considering a really small volume omega. Then that can be easily approximated as what? Approximated as just multiplying the volume and multiply just divergence of Fc. So by eliminating the omega from both sides, then we can find the final form like this. Okay, the time derivative of our carrier density is simply given by minus times divergence of our carrier flux. That is the general form of our continuity equation. So both for electrons and holes. Wow. So could you please copy that? You have understood all of my discussion up to now. Then let's just write down the answer. So round n over round t now becomes minus divergence of electron flux. Then another one is now for this whole carrier, then round p over round t equal to minus whole flux. Okay, everybody will be happy with this form. However, usually we don't adopt this. Of course, it depends on the situation, but usually instead of a flux itself, we have an alternative quantity called, this is just the electron flux, and this one is a whole flux. So carrier flux. However, we wanted to switch the two current density. So what is the difference between them? Flux is just counting number, and the number per unit area and unit second. However, now current density is the ratio of transferring the charge. So instead of this flux itself, we now say that C coulomb per unit area and unit time. And you know that the physical unit, which is given by coulomb per second, it has its own name. So you know its name. That is ampere. So now we have this form. So you can easily understand the relation between flux, just carrier flux, and carrier current density is related with this difference. So previously we just count number. However, now we have to consider the charge carried by that charge carrier. So in the case of electron, so each electron just carries minus q. In this lecture, q is regarded as positive 1.6 times 10 to the minus 19 coulomb. So the electron's elementary charge will be written as minus q. So sometimes people prefer to have something like this, E, and in many cases it is just written as 1.6 minus ES, the real elementary charge carried by our electrons. But please, in this work, following many other engineering literature, we'll just use minus q for representing the elementary charge of electrons. Okay, then since electron just carries minus q, in order to convert our electron flux into the electron current density, then usually we have to do in this way. Jn, the electron current density, is given by Fn, electron flux, multiplied by minus Q. Yes, that's all. And how about hole? In the case of a hole just carries, instead of a minus Q, it carries a positive Q. So Jp equal to positive Q multiplied by, yes, F sub P, so hole flux. Then, since we have two different or the opposite signs for minus Q and positive Q, when we just evaluate this right hand side term in terms of J sub n, we will have a little different form. So in this case, we will have 1 over Q Jn. That will be the form, and in this case, yes, that will be the form we will consider. Okay, so now let me summarize the discussion up to now. So up to now we just introduced the Poisson equation, and you know it, and electron continuity and hole continuity equations have been introduced, and their final form just looks like this. So here have three equations. Okay, so when solving them all together, then we will have the solution of the drift diffusion equation. Of course, I wanted to stress that the things are not finished yet. So for example, usually, since the equations are, the number of equations is 3, so we have to consider 3 different unknown variables to make it complete or determined. Then usual choice is now electrostatic potential phi, and electron density n, and hole density p. They can be selected as 3 unknown variables, and when we have a look at this equation, then yes, this is an unknown variable, and minus epsilon, this is material dependent parameter, and you know it. And law, okay, here law we need a little further discussion. However, law can be a sum of contributions from electrons and holes and dopants. So we can think that law, the net charge density, is given by minus q times n, and positive q times p, and finally positive q times positively charged dopant. Okay, so of course, if we have a negatively charged dopant, then this n plus quantity can be negative. For example, if we have n-type dopant, then that will contribute a positive number to n plus quantity, n plus doping quantity. And if we have a p-type dopant, then that will contribute to negative value for this capital N plus quantity. Okay, you can easily understand this one. But my point is, yes, we have 3 terms, and you know that this N plus is just a given number when we have the given structure. So anyhow, that is given, and you know, n and p, they are unknown variables. So when you consider the Poisson equation, Poisson equation can have dependencies on phi, n, and p. Yes, it's okay. And also it can have a dependence on n plus, however that is given, and it can have a dependence on epsilon, but that is given. So everything is quite clear. Then when we go to the continuity equations, so here we can find the electron density and hole density. Yes, they are again unknown variables, then it's okay. But when we have a look at the right hand side, the most right hand side, rightmost side terms, then you can find that this is j sub n and j sub p. What is it? So we have no idea about the functional form of j sub n and j sub p, and in order to make this system as determined, then we have to say that this j sub n and j sub p should be written as a functional form on phi and p. Also that should be represented as functional form of phi and p. So that is the missing discussion up to now. So I just once again pause here and wanted to ask you whether you have any question up to now. Okay, so okay, Mr. Han, you ask me the meaning of, explain once again the meaning of n plus here. Okay, thank you. And you know that this n plus, that is not the standard notation, so yeah, it's okay. Let me just write down once again. So to be more accurate, or I have to write down in this way. Okay. So let me just copy our left hand side term. Okay. Then now think about this low term. This low term can be decomposed into the contribution from electron. You understand? And now you can consider contribution from hole. Then how about the contribution from, for example, donors? And how about the contribution from acceptor? So we are now assuming the full ionization of donors and acceptors. So when we assume the full ionization, donors contribute positive charge and acceptors contribute negative charges, and each donor contribute positive Q and each acceptor contribute negative q. So that will be the most standard expression for our law. But instead of having these two terms from the dopant density, sometimes people make a short-handed form like this. Just to consider positive Q and N donor, yes, that will be positive, and minus N acceptor. Then let's call this difference between these two quantities as just n plus whatever. So you may introduce any subscript, proper subscript for your better understanding. But anyway, here when I say n plus, yes, that is corresponding to the difference between donor density and acceptor density. So of course, when we are talking about n-type region, then n plus will be a positive number. And when we consider a p-type region, then we will have a negative number. Okay. Okay. Thank you for good question. And now let's come back to our main discussion. Oh, so up to now, we just introduced three equations required for the drift diffusion model. And now you understand they are Poisson equation, although that is not exactly Poisson equation, but anyway, Poisson equation, and electron continuity and hole continuity. And when we say electrostatic potential and hole electrostatic potential and the electron density and hole density are unknown variables, then although this system looks great, but we have still a question. So what is the functional dependence of our electron current density and hole current density? How are they written as functions of phi, n, and p? So that will be the next question we have to understand. Okay, so usually in our lecture for computation lecture or in previous years, we have spent quite a long time about explaining how can we derive this j sub n and j sub p, mainly j sub n, from the Boltzmann transport equation. You know that we have a well developed methodology to have the exact equation. Exact means that some of course exact means that we have to be a little bit careful about the terms like exact. So but anyway, the derivation of the form of Jn and Jp, that is known to us. So we can make the derivation systematically from the Boltzmann transport equation. But in this semester, our focus is not in the mathematical rigor, but we are now more interested with implementation and many capability related with the computational microelectronics. So I will not spend much time on these important and interesting steps. So if you are really want to be an expert in the computational microelectronics, you must master that derivation procedure, of course. But if you are just considering the implementation for a while, we can just quickly introduce the resultant equation. Okay, but please note that skipping that topic does not mean that you don't need to learn or study about the derivation procedure. So that is my caution. So anyway, I will just go to directly the final form of J sub n and J sub p. So J sub n, this is electron current density, and this J sub p, that is the whole current density. Then the reason why we call this coupled system as drift diffusion, actually that is originated from the functional form of our J sub n and J sub p. So although it sounds really confusing, but when we just consider these three sets of equations, that is not related with the name called drift diffusion. Where can you find the drift term? Where can you find the diffusion term? No, it is not found in this form. All of drift and diffusion, the physical mechanism to transport our charge, is just hidden in this Jn and Jp terms. So now we go to this Jn and Jp. So simply speaking, we can think about another model for charge carrier and another charge transport, and another model, yet another model for charge transport can be invented. However, this electron continuity equation or hole continuity equation is, they are general equations, and only difference can be made in this functional form of J sub n. Please do not try to modify your continuity equation itself, because when you have a look at the derivation procedure of our continuity equation for electrons and hole, you can find that that is really rigorously derived, and no approximation is available in this continuity equation. However, if we have a look at the derivation procedure for J sub n and J sub p, in this case we have introduced many approximations related with the band structure mainly, so or distribution function of our electrons and holes. So therefore we have still some rooms to introduce a different form of J sub and J sub p. But anyway, we will just stick to the simplest one, the drift diffusion one. So the name, the drift diffusion, is related with drift and diffusion. So we will just introduce two terms related with drift and diffusion. Of course, even for holes, we will introduce two terms, drift and diffusion. So let me just write down in this way. So it is given by the drift term. So I think that at least since your major is really related with this computational microelectronics, you have to memorize, or you have to remember this form. And when we consider whole current density, then of course this subscript or charge density should be changed to whole. So Q mu P P E. That is the drift term for holes. Then when you go to the diffusion term, so in the case of electron, then we will have dN, electron diffusivity, and gradient of electron density. And in the case of our hole, then now we have this form. So let's have a look at here. We have a negative sign. So sometimes people are confused by where can we introduce some negative sign or positive sign, something like that. So please try to memorize it or remember it, the correct position for minus signs. But anyway, this is the form for our electron current density and or current density. Of course, if we just apply the electrostatic approximation for our electric field, then we can introduce a more frequently used form or more suitable for our purpose. So in this case, then we will have minus q mu n and yes, so gradient of phi and q d n gradient of n. So also in the case of hole density or hole current flux, then we will have minus q mu p p and gradient of phi minus q dp. Yes, so you know it, and please remember these forms. So do you have any question? Okay. Then let's go to this form once again. Now let me just concentrate on the electron current density, and hole current density can be treated in a similar way. So let's just have a look at it. Okay, so this is the form we will have from now on. Then it has many interesting properties, but in this lecture, uh, let's think about the equilibrium properties. Okay, so equilibrium, at equilibrium, what we have to do is, since this is equilibrium, there will be no current conduction. So simply speaking, yes, equilibrium case, we have to have 0 J sub n. And in this case, now we say that minus q mu and yes, gradient of phi plus q dn. I'm just repeating the functional form of J sub n once again, and they should be 0 everywhere. I mean that everywhere. Every point in our device, we have to have this relation. That is the condition for our equilibrium. And of course, we can make a real simplification, like eliminating q. Yes, because we can just divide our left hand side term and right hand side term by positive q, but still we have the equality. Then we will have just minus mu n n, and yes, we will have also this form. Yes, this is strictly valid. And also now we have to introduce another rule called Einstein Relation. So in this case, simply speaking, at equilibrium, I'm not urging that this is a general relation, but at equilibrium, we can say our diffusivity can be written as the form of mobility. And here we have summer, how can I say, let me just write down explicitly, summer voltage, kBT over Q. Usually this quantity which have the voltage unit is called as summer voltage. And if we have this only this upper part denominator, then this is summer energy, but usually we just use summer voltage in our context. So if we just introduce this special relation which can be applied to the equilibrium state, then we will have, instead of this dn, now we will have, yes, kBT over Q and d, oh sorry, not dn but mu n. So although mu n can be a complex parameter, however, if we have mu n and mu n in both sides, then we can safely, yes, and dividing the left hand side and right hand side by mu sub n, then we will have a much simplified form. So why don't you just write down here, so in upper part, okay, if we just write down here, then it will just read equal to kBT Q over n equal to 0. So you know it. Then why don't you just move our term into here? Then instead of this form, then we'll have yes, not that difficult. And another one we will have is, okay, this n can be divided, then we will have this form, kBT over Q and 1 over n gradient of n equal to gradient of 5. Then if we have a look at this form, you can easily understand this is corresponding to gradient of log n. So gradient of log n is simply given by 1 over n gradient n. Oh, the same as before. So you remember this relation independently with this context. So you can write down in this way. So simply speaking, let me just write down in this way. The entire equation can be now written as this form. Gradient of our log n equal to gradient of our potential divided by kBT over Q. This is constant, and yes, this guy come to here. Yes, that's it. So these two quantities, so log n and phi normalized by kBT over Q, have the same gradient. Then what does it mean? It means that, okay, since they have the identical gradient, so we have only a freedom that the constant difference between them. So log n can be written as, yes, over q n plus something. Yes, I have no idea. There will be a constant difference between them. So now let's just merge it into, since we have no idea about how the constant looks like, but let's just keep going. Then if we take the exponential of this form, the left hand side and right side, then we will have exponential log n. You know it, that is just given by n. Then how about the right hand side? Then we will have exponential n phi kbt over q plus, and the constant we have introduced just yes. Then now the answer will be electron density is given by exponential phi divided by kbt over q multiplied exponential certain constant. So we have no idea about what is it. However, from the physical consideration, now we call it means that this guy as intrinsic carrier density. I have to say that usually standard way to write down the intrinsic carrier density is n sub I. But since we are talking about so many times n sub i's, about the i's nodes in electron density, so in order to make a distinction between two different quantities, I just introduce a longer name like n sub int. But you know that in reality, in this field, n sub I is more frequently used to design or designate the intrinsic carrier density. Sometimes we add more like this. So Ni effective, so effective intrinsic carrier density, but this is not the case for our discussion. So anyway, following this relation, then we will have this form. So n is proportional to intrinsic carrier density and exponential phi over kbt over q. And you know that usually this one is called as, once again, summer voltage. So now if we just write down the summer voltage as V sub t, then we will have an int exponential phi over V t. That will be the answer, or that will be the relation which can be directly derived from the equilibrium condition. So what we have done is just to assert that J sub n should vanish at everywhere. If we just assert that that condition, then quite naturally we get the solution like this. Electron density should be exponentially dependent on the electrostatic potential. So now when you repeat this one to our system once again, then you will find that hole density is simply given by at equilibrium and intrinsic carrier density, the same intrinsic carrier density, and exponential minus phi over Vt. Okay, they have the opposite sign here. This is positive and this is negative. So please note that this relation and this relation is a specialized form of electron continuity and hole continuity. So using this information just equivalent to solving the continuity equations, at least at equilibrium. Of course, for non-equilibrium case, we cannot use this form. You remember that in order to make this form, we have introduced J sub n should vanish, or J sub p should vanish. So that is really applicable only at equilibrium case. But at equilibrium case, this is identical with the continuity equation. So in our first case at equilibrium, then what we have to solve is now reduced in this way. Okay, minus epsilon phi equal to, yes, once again rho, and rho can be minus qn positive qp and positive q and plus due to doping, so whatever. So, and instead of using these two continuity equations, then we can just say n is proportional to the exponential of phi, and hole density is proportional to exponential of minus phi, of course normalized. Then when we test this system once again, then we can find, let's call phi and p as unknown variables, and let's try to test them. Here, yes, this is an unknown variable, and this is unknown variable, and this is unknown variable. And let's go to the second equation. Yes, this is unknown variable, and this is unknown variable. Third one, hole and phi. They are unknown variables. And how about other one? This guy, that is a given parameter, and of course minus q, that is given parameter, or universal constant. And here doping density, yes, this is also given parameter, and intrinsic carrier density, that is also given density. And when temperature is given, also our summer voltage is given. In this case, the system is really containing just dependencies on given parameters, or electron density, hole density, and electrostatic potential. They are unknown variables. So that system is really determined, and you can solve it. So my today's homework number 10 is posted from now on. In this homework 10, just try to solve the system shown in the left side. Okay, so you can immediately understand this is the equivalent form to our non-linear Poisson equation, you know it. That is actually the nonlinear Poisson equation. But my suggestion is, please do not introduce more compact form usually adopted in our computational microelectronics book. I mean that just inserting this expression into here and inserting this expression into here, then we can completely eliminate n and p from our unknown variables. Then we will have just a certain equation which contains just phi as the only unknown variable. However, please do not follow that way. Just keep electrostatic potential and electron density and hole density as three equations, and please try to solve this system. And in order to make your life easier, then I do not urge you to solve this system for every device, but please concentrate on a certain double gate structure we typically use. For a certain double gate structure, so detailed information can be obtained from our previous lecture in 2020 or other years. And yes, for that typical double gate structure, please try to solve this coupled set, the set of coupled equations. So do you have any idea or do you have any question about homework number 10? So then please let me know. Simply speaking, I just asking you to solve the nonlinear Poisson equation. Actually, not exactly nonlinear Poisson equation, but which is equivalent to the nonlinear Poisson equation. But please keep our unknown variables phi and p. Then you will have more equations, although two of them are just trivial. But anyway, please keep these three unknown variables. It is because once after we have built such a three unknown variable system, then it is easy to switch it to real drift diffusion model, which can be used for our purpose. Okay, so then finally I once again asking you any question for our okay, so please Mr. Park, please go ahead. Yes, sure. So in your Jacobian matrix, your Jacobian matrix, you have to have phi and p appearing at the same time. So please make the fully coupled implementation. So Mr. Park, so are you with me? Do you understand the meaning of a fully coupled implementation? So here we have phi and n and p, and please do not, for example, fix some of them as a given number and solve one variable. After that, solve another variable sequentially, then expecting that system will be eventually converged. Of course, that is another way to have the converged solution, but I'm not talking about such kind of so-called Gummel type iteration method. I'm just asking you the fully coupled scheme. So in in this system, you have to have three unknown variables simultaneously, and three equations should be placed also simultaneously, and all functional dependencies should be considered exactly. So that is my question, or that is our homework number 10. So Mr. Park, are you with me? Or if you don't understand, then please ask me. Okay, then, okay, so I will just post our homework. But anyway, this written uh, language, or this verbal posting is enough to you. So please understand the homework number 10 is posted now, and in this case you have to solve this coupled system which is valid at equilibrium. Okay, so thank you for your participation, and see you this Thursday. Okay, so I hope that homework number 10 is not that difficult to you. If you have any question during doing that homework number 10, please let me know. Bye.